Hey everybody. Today we're doing an example problem using a joint distribution of two continuous random variables. Here's the problem we're going to work on. A 1 meter piece of rope is cut at a random place with uniform probability, and then the first part of the rope is cut at another random place, again with uniform probability. Suppose x and y are the positions of the first and second cuts respectively. We want to find the joint probability density function of x and y. We want to sketch the support, compute both marginal and both conditional PDFs, and then finally, compute the probability that x is less than or equal to 0.75 given that y is equal to 0.5. In other words, we're going to assume that somehow we know the position of the second cut, and we want to say something about the probability of where the first cut might be. Let's start with those uniform distributions that we're told about. X is uniform on the interval 0, 1, so its marginal PDF has to be f of x is 1. Remember, the PDF of a uniformly distributed random variable is 1 over the width of the support. Since y is uniform on the interval 0, x, where x is previously determined, its conditional PDF is h of y given x is 1 over x. 1 over x being the reciprocal of the width of the interval that's its support. We can then combine those two facts using a multiplication rule. F of x, y, the joint PDF, is equal to h of y given x times f sub x of x. So that's just 1 over x. The joint support is x between 0 and 1, y between 0 and x, which makes sense if you think about cutting that rope twice. Here's a sketch of the support. It's just a triangular region. Now, I've shaded it equally from left to right, but since the joint PDF is 1 over x being larger for smaller x values, the probability density is greater further to the left. So it might be nice if this were a little more opaque to the left and a little more transparent to the right. Now we can also describe the support by different inequalities, basically writing y first, making x contingent on y rather than the other way around. So y between 0 and 1, x between y and 1. All right, now we're ready to compute the other marginal PDF, f sub y of y. Now, we get any marginal PDF by taking the joint PDF and integrating over the other variable. So first we need to know what range to integrate over. For any y between 0 and 1, we said on the last slide that the range of possible x values is between y and 1, so we're integrating that joint PDF, 1 over x, from x equals y to x equals 1. When we carry out that integration, find an antiderivative, which is going to be the natural log of x, then plug in the endpoints and subtract, we get negative ln of y. Notice that this is always positive since y is between 0 and 1, so the natural log of y is negative. You can also check directly that if you integrate f sub y of y from y equals 0 to y equals 1, you do get 1. So this really is a legitimate probability density function, as we would hope. Now we're ready to compute the other conditional probability density function, g sub x given y. By definition, that's equal to f of x, y, the joint PDF, divided by f sub y of y, the marginal PDF for the variable that we're conditioning on. Plugging in things, simplifying just a tiny bit, we get negative 1 over x times the natural log of y. Again, y between 0 and 1, x between y and 1. So, for instance, when y is equal to 0.5, we can just plug that in. We get g of x given that y is 0.5 is 1 over x ln 2. X then has to be between 0.5 and 1, 0.5 being the value of y that we're plugging in here. G of x given y is also a legitimate probability density function. For instance, when y is equal to 0.5, g is 1 over x ln 2. And if we integrate that over the range of possible x values for that given y, so from 0.5 to 1, we get 1, just like we'd hope. Additionally, 1 over x ln 2 is positive for all those possible x values. This is, of course, true for any other y value that we would use between 0 and 1. So let's wrap up this video wrap up this problem by computing this probability that x is less than or equal to 0.75 when y is equal to 0.5. So we're going to integrate g of x given 0.5, which we just found, over the specified range, probability that x is less than or equal to 0.75. That means integrating from 0.5 to 0.75. 0.75 on top, coming from that x less than or equal to 0.75. The 0.5 on the bottom, coming from the fact that y has to be less than or equal to x here. When we do out that integral, we get about 58.5%.